Okay, so we start at 11:45, right?
45, yes.
All right.
That's me.
All right, so we're going to get started in about a minute or two. Welcome to session 5B, Emerging Technologies. We have 5 great talks lined up for you all. The first talk is going to be given by Bingzhe Li. He is an assistant professor at University of Texas at Dallas. He is broadly interested in storage systems and will be presenting his work on encoding information for DNA storage platforms. And and just to give you an idea of the format, there will be 12-minute talks, and then we'll have 3 minutes of questions. And then you can always catch the speakers after the session, up front or just outside of the room. So without further ado, I'm going to go ahead and let you take it away.
Thanks, Sarah's introduction. So today I'm gonna introduce our work encoding scheme to enlarge practical DNA storage capacity by reducing primer-payload collisions. So here are the outlines of this talk. So first of all, I will cover the introduction and the motivations of this work, and then introduce the background of DNA storage, like what is DNA storage, and then I would like to introduce the collision-aware code algorithm for DNA storage. After that, I will show some experimental results and then the conclusions. So first of all, the challenges of existing archive storage. So based on the International Data Corporation predictions, the total amount of data in the world will reach to 32 zettabytes by 2030. So there's a really huge gap between the existing storage systems and also the storage supplies. So basically, the supply of storage cannot catch up with the increasing demand. Also, the existing storage medium cannot preserve data long enough. So for example, for the traditional storage devices like magnetic tapes, so it has about like up to 15 years lifespan, the hard disk drive about 3 to 5 years, flash memory about 5 to 10 years, right? So that means after this amount of time, so the data has to be migrated to a new drives, and then it's kind of increase the maintenance cost. So you do need to replace those old storage devices with new ones, right? So DNA storage is a promising device as archive storage medium due to 2 advantages. One is DNA storage has really long durabilities. And secondly, DNA storage has really high area densities. So for example, ideally, DNA storage can improve the area density by 1 million times compared to the traditional storage devices. And also, DNA storage can be preserved more than hundreds of years. So because of these 2 advantages, DNA storage is really promising storage devices for the archive system. So what is DNA storage? So basically, there are 4 basic nucleotides or bases in the DNA, AT, CG. AT associated with each other, CG are bonded with each other. And for the read and write process of DNA storage, first of all, we have binary data, and then we need to encode the data into the ATGC sequence. So based on the right table here, you can see the simple encoding, you can encode 00 to A, 01 to T, 10 to G, and so on and so forth. After that, you need to assign some like primers or metadata, like the internal index or ECC code, error correction code, attached to the payload. And then based on some synthesis process, it's kind of biotechnologies, you can convert all those DNA strings into molecular form. On the other hand, to read data out, so first of all, we have sequencing machines. We can sequence the data out like nanopore next generation sequencing. So then we get the ATGC sequence, and then we do need to extract this payload information and then decode the data back to the binary data. So this is the basic process of DNA storage. And then we can store the DNA strings into a single tube or maybe multiple tubes. So there's millions of maybe DNA strings in one tube. So here are the 1 definitions of DNA storage capacity, which is how many data we can store in the one single tube. So here's another concept of the technologies in the DNA storage, so-called the PCR, and also the random access. I think during the pandemic, people kind of become familiar with the PCR process, which is try to do the COVID virus testing. So the basic ideas of PCR is try to amplify the target DNA strings from for the random access in the storage system. So for example, if we have millions of the DNA strings in one single tube, but you want to read the target data out. So based on the PCR process, you can just amplify the target strings with multiple iterations. For example, after 10 iterations, the number of the target DNA strings may be increased 1,000 times, right? So the basic idea for the PCR, you do need to use the primer as an index or maybe the ID. So then based on that, you can do the random access for the DNA storage. So the factor affecting the tube storage capacity, I would say this is one important contribution of this paper. We identify the factors which affect the DNA storage tube capacity. So here, the tube capacity equal to the payload encoding density, multiply the payload length, parallel factors, and also the number of usable primers. So for the first three terms here, it's restricted by the current biotechnologies. And for the number of usable primers, of course, there's a kind of the standard rules to design those primers. So one thing we found in our paper is the primer-payload collisions have really huge impact on the number of usable primers. So based on the result, the initial investigation here, the influence of payload primer collisions, you can see if we want to store more and more data into the tube, DNA tube, and the number of available primer will drop from around like 20,000 to 10,000, right? And then the tube capacity actually around 200 gigabytes based on the rotation encoding. For other state-of-the-art encoding schemes, so maybe the tube capacity only have hundreds of megabytes, so which is far from the expected DNA storage capacity. So to mitigate the issues of the payload primer payload collisions or try to improve the tube capacity of DNA storage, so we propose a collision-aware coding schemes. The idea is we try to trade off the encoding density and also the payload primer collisions. So here are some basic ideas or rules of the primer sequence design and also the payload sequence design. So here I just want to mention, first of all, for the payload sequence pattern, so we don't allow the homopolymer. Homopolymer means AATT, GGCC, such kind of the identical patterns. And also for any 20 base pair sequence, we should have fewer like consecutive complementary sequence and also more balanced GC content. Okay. So here's a little bit details of the CEC design. So first of all, we have the binary data, and then we group like 3 digits together, and then we design a mapping table to encode the binary data into the nucleotides. And so basically, we look back at the last base. So try to avoid the long homopolymer with the last base, and also look back on the previous 17th base to avoid this kind of the complementary sequence and also try to balance the GC contents. So here's a little bit details about select the DNA triplet from encoding table. So first of all, initially each bit triple have 4 candidates based on the proposed mapping table here, and then we need to follow some rules to encode the data. So first of all, we need to avoid the homopolymer, and then we consider less complementary sequence, and then strict balanced GC contents. So for example, if we already have like 17 spaces, and then we try to encode 0, 1, 0 here. So there's a 4 candidates like ACT, AGT, TGC, and GAC. For the first 2, is from the homopolymer with last base. So that means we won't select these 2 candidates. For the last 2, is past the homopolymer check, and then we go to the next check. So for the complementary sequence check, the third one have 4 like complementary sequence, but the fourth one have only 3. So we just select the last one as the candidate. And that means we will encode 0, 1, 0 into the GCT in the DNA storage. Okay, and here is some like encoding table design rules. So principle 1 is no internal homopolymers based on the bio constraints. And then we need to use the different starting bases and also the complementary pairs in the mapping table. The last one will be the GC balance candidates. So all those principles are following the bio constraints in biology domains. here's the experimental result. So for the capacity and also the number of usable primers. So there are three schemes: rotation, which is the state of art, CC is hours, and exhaustive search is kind of the upper bound. Based on this figure, you can see we can double the number of available primers compared to the state of art. And then for the capacity perspective, we can increase the capacity about 14%. So the key idea here is like we balance the balance between the encoding density and also the collision avoidance. Okay, here are the conclusion of this work. So first of all, the practical tube capacity is much lower than the expectation, and we propose a new collision-aware encoding to improve the capacity. And the new mapping table is proposed based on our evaluation. We can improve the number of primers by 2 times and the capacity by about 14%. Okay, thank you, and feel free to ask any questions. Yeah. Questions?
Instead of other molecules like RNA, because like is it because DNA has some kind of fundamental like properties that enable like storage more trackable? Or
I think maybe the one I think it's a good question. So maybe one of the answers or the advantages of the storage DNA is like maybe stable. So because we want to preserve the data in DNA storage for maybe more than hundreds of years, right? And DNA probably is kind of more stable than some other ones. Yeah.
Yeah, thank you.
Yeah, thanks for the question.
Can I see? Okay, cool. Do you have to worry about secondary and tertiary structures of the DNA? at all?
Yes, yes.
Like hairpins or?
Yeah, hairpin structure, secondary structure. Yes, this is kind of the one factors or bioconstraints have. But even though we have this kind of the hairpin or secondary structure in the DNA strings, but based on the ECC or some like technologies, we still can correct all those data. So based on some papers like Louis's paper, so they do the wet lab. And during their encoding scheme, they didn't consider this kind of the hairpin structure, secondary structure, but they still can retrieve all those data from DNA. Yeah. So, but this is kind of really important factor. So maybe in the future work, we need to consider this kind of things during the encoding, converting the data to the DNA. Yeah.
I see. So you stack like other sorts of methods to.
Yeah. So far, I think all the encoding schemes don't consider this kind of pattern during the encoding, but in the future, I believe we should consider that to make sure the error rate can be further reduced. Yeah.
Okay, and the evaluation was in simulation or was it in a wet lab?
So far our work is based on the simulation, but also those kind of, we use some biotools to generate the primer. So those biotools are really commonly used in the biology areas. But the next step will be like, currently we are doing, we are collaborating with the industries, and then we try to do some wet lab for the validation purpose. And also because the DNA storage is really expensive. So if you evaluate, for example, 200 gigabytes data stored in the DNA and then retrieve all those data, maybe cost $1 million, more than millions of dollars. It's really expensive. Yeah.
Yeah. I see. Thank you.
Thank you. Yeah.
Other questions? And if the next speaker could line up actually and get set up.
Yeah. Thanks.
Okay, so while our next speaker is getting set up, I'd like to introduce Yu-Neng Wang. He is a third-year PhD student at Stanford University. He is broadly interested in software systems for analog computational substrates and will be presenting his work on codifying analog compute paradigms in analog design spaces. And we're running a little bit ahead, but we'll go ahead and maybe wait a minute or so and then get started just in case people are filtering in and out. And so you can start at noon. And then I'll start the timer. I'll give one.
Yeah.
Most okay during the test. Okay. Okay. Hi, everyone. I'm Yu-Neng from Stanford University. Today, I'm going to share a bit on how to design novel analog compute paradigms. So we'll start with a brief introduction to analog computing. First, what is an analog compute paradigm? It means that instead of using discrete 0, 1 values, we use continuous quantities to carry information. And novel means that in contrast of classical analog computing, we use the unconventional part of the signal to perform computation. For example, transmission line computing uses the transient dynamics of wave to do computation. Oscillator-based computing uses phases to carry information and perform optimization. And chemical reaction network repurpose chemical reaction to do arithmetic calculation. There are many ways to implement these computations. Among them, analog circuits naturally implement analog computing, where they use electrical signal to represent continuous quantities. The benefit of analog circuits is that they can be made very resource efficient, and they can convert physical information to electrical, allowing them to interact with the physical world. So why are we interested in analog computing? The reason is that if we combine novel analog computing paradigms and analog circuits together, they are a promising building block for the future hardware platform. First, novel analog compute paradigm supports a variety of computational tasks, such as physical simulation, optimization, and signal processing. Meanwhile, analog circuits are resource efficient, making computation affordable everywhere. And combining analog compute paradigms and circuits together allow us to process physical world data at the source, reducing data movement. However, why is it the future, not now? It is because analog circuits have so-called non-idealities that change the execution of the circuit in a random way. Simply speaking, what you set is not what you get. To make sure all these non-idealities won't sabotage the hardware execution completely is not trivial. Current novel analog accelerators try to be general purpose, meaning that they have to consider non-idealities in a huge space, which often results in the overly conservative design and incur a high resource cost. However, classical analog circuits like sensors and amplifiers are very resource efficient. How so? Because they limit the programmability and specialize analog circuits for the application domain. Therefore, designers will want to specialize novel analog circuit as well. However, co-design a compute paradigm with the circuit is extremely difficult, mainly because they are unconventional, so we don't have a good modeling techniques and design guidelines. Therefore, we propose our programming language ARC to help develop novel analog compute paradigms. In ARC, designers can rigorously model analog compute paradigms and analog circuits as a domain-specific language, and writing the program in the DSL is like co-designing the paradigm with the circuit. The design procedure is progressive, meaning that users can easily add or modify the DSL to incorporate new analog behaviors as they gain design intuition or guidelines during the design process. Overall, ARC enables design space exploration of analog circuits that use novel analog compute paradigm, allowing practitioners to optimize their design. So how do we achieve this exactly? There are two key points that make ARC work. First, we found a unified abstraction for novel analog computations and formulate in the ARC language. Therefore, designers can use a language to model each paradigm as a DSL. Specifically, an ARC DSL defines the design space of analog compute paradigms with the space of parameterized type graph, which I will go into more detail later. The end user can simply write a program in the DSL as a type graph to implement computation in the specific compute paradigm. ARC also comes with a validator and a compiler, where the validator will perform checks based on the DSL to make sure the graph is well-formed. and the compiler will compile the program into a dynamical system that is executable. Users can base on the execution results to perform DSE. Beyond modeling the computation, it is also critical to consider non-idealities in hardware realization. So the second key feature of ARC is that we can also specify design space of analog circuits considering non-idealities. For example, given a specific hardware implementation, analog designer can define hardware extension to analog compute models that capture design trade-off and non-idealities in the circuit. These hardware extensions provide a rigorous description of design space associated with a particular hardware realization. And with this extended DSL, end users can again write analog computation as a type graph and using the hardware extension and perform DSE with non-idealities being considered. So with these two features, what does an ARC program represent exactly? So to be more specific, a program specified in ARC language should be thought of as an executable specification that can be plausibly implemented in the transistor level because they follow the hardware extension written by analog designers. What can ARC do exactly? First, we would like to emphasize that it is not an analog circuit synthesis framework that goes all the way down to transistor sizing and layout. Instead, we target early design phase to help making decisions in higher level manually. For example, like which part of the circuit should be programmable and identify architecture and high-level parameter values, and to what extent non-idealities can be tolerated or even be useful. Let's now look under the hood. Why do we choose graph as the unified abstraction? We're going to argue that it is actually very natural. To see that, let's first observe that analog computing is fundamentally governed by structured ordinary differential equations, where we have the derivative of the state variable on the left-hand side of the equation, and algebraic equation consists of state variables under a specific pattern on the right. For example, in transmission line-based computing, the pattern is that V-type state variables can only affect neighboring I-type variables, but not the other V-type variables. Analog circuit implementation will modify the differential equations form and their parameters. If we use GNC integrator to implement, then we have extra weights, and also they might have random mismatch, so the parameters will become Gaussian random variables. Observing these structure, we decide to model the analog compute models with typed graph in ARC, where the graph components denotes the variable and their data types in ODE. Connection have patterns. Also, they are based on the structure of the ODE. For each node, it looks at its neighboring node, edges, and their types to map to an algebraic equation. Together, they are sufficient to describe the analog compute model. So you can think of an ARC DSL as a language that specifies all the types, connection rules, and mapping rules used for an analog compute model. Moreover, because non-idealities are like small deltas, we use inheritance to model them. Here, to model a GNC integrator, we let the edge to have additional attributes to model the weights, and the rest of the differential equations are the same. Also, if you want to model non-ideal weights, simply inherit the edge and make the weight attribute become a random variable. Lastly, because the analog compute model fundamentally is a system of structure ODE, the structure is useful and we should keep track of it. A graph captures the structure explicitly. You can see that we have a correspondence between the computation and the dynamical graph. And if we want to stick together computation, we can easily manipulate them as operation over graph. Together, designers can construct graphs representing computation and selectively modify topology and introduce non-idealities to explore the design space. Here are the results. We're going to present 3 case studies that we do design space exploration with ARC. The overarching goal is to show that ARC can model distinct analog compute paradigms and is able to codify the design space considering analog circuit non-idealities. The first example is using transmission line-based computing to implement a physical unclonable function. I won't go into detail of what the function is, but roughly speaking, the goal is to make the function output very sensitive to random mismatch in the circuit. It is very unconventional in a way that we actually want to amplify the effect of these non-idealities. We can explore topology and programmability first. Let's introduce programmable switch and observe the tension dynamics at the output node. When the switch is on, because the wave splits to the branch and reflects back, we see a second pulse coming shortly after the first one. And this is consistent with the intuition from observing the topology. We then selectively introduce different kinds of mismatch to understand their effect on the computation. We model two mismatch as a node type and an edge type that inherit from the compute model, make the same topology, and observe at the output again. From the simulation, we can see that although they both are non-idealities, their impacts to the dynamics are very distinct. In the application we target, designers can distill this into a design insight and prioritize amplifying GM mismatch to achieve mismatch-sensitive transients. The second example is the cellular nonlinear network. The compute paradigm can be used for signal processing. Here we show an edge detector that, given a figure, the variable in CNN gradually evolve such that only the edge in the figure has non-zero value. We introduce random parameter mismatch, and we can see that the edge detection performs poorly. Separately, if we introduce non-idealities to the activation function, the edge detection actually settles faster. Designers can further investigate the root cause of this phenomenon and inform their decision. The final example is oscillator-based computing. The differential equation governs the phase dynamics of the oscillators. They can solve optimization problems such as max cut. We model a non-ideal bias to the phase dynamics, and it turns out the oscillator won't be able to synchronize perfectly, so it fails to solve max cut. However, if we relax the measurement to allow wider range to be considered as synchronized, then we can achieve solving max cut in the same level of accuracy. The three examples demonstrate how ARC helps modeling non-idealities during DSE, which can significantly affect designers' decision in the early design phase of novel analog compute paradigms. In conclusion, ARC is a language for design space exploration of novel analog compute paradigms. It provides a unified abstraction and can specify analog design space for non-idealities, letting users to explore the design phase. We also demonstrate, and finally, we would like to go back to our motivation. We hope our tool can inspire more collaborations between analog designers and domain specialists, and together create a brand new future hardware platform. Thanks for listening, and feel free to ask any question.
All right, please line up if you have any questions.
Hi, I'm Kevin from University of California. Nice talk, and it's really exciting to see this. I had one particular question about the ARC compiler. Can you just give us some idea of what the formats or tools are that you compile to?
Oh, yeah. So with the DSO, it specifies how a graph should map to differential equations separately. So the compilation is that taking those rules, I map a graph to a set of differential equations where the left-hand side are all the derivative term, and the right-hand side are like composing graph components that map to certain like algebraic equation. So in the end, it will be like a system of ordinary differential equations, and it's like can be simulated with whatever numerical method you like.
Okay, thanks.
Hi, Gus from the University of Washington. This is an awesome talk. Thank you so much. I'm really curious about, I know you said that you don't do synthesis, and I'm not, I'm just curious, what would it take to do synthesis? It's a problem I think about a lot. So
so yeah, we're not doing synthesis, and the reason is that to make sure I understand your question, you're asking what an analog synthesis is.
So what would it take to actually compile down to analog circuits? It's from what I can tell, you were mostly simulating existing circuits. How would you actually go from a high level specification and compile to these analog devices?
I will answer this in twofold. So in our method, we're like asking analog designers to collaborate with domain specialists. So domain specialists just draft designs, and then analog designers should do the manual design, the circuit transistor sizing part by their hand manually. And the reason we do that is because of a second reason. There's a tons of work in the previous like maybe 20, 30 years trying to do automatic analog synthesis. But because of all the art, like there's a lot of design intent, they call design intent in the analog design. So like the automatic tool never succeed like in reality. So that's why we aim to provide a sort of better manual method for them.
We should talk offline. I would love to talk more about this.
Yeah.
Thank you.
John Demi, Microsoft. How, in your experience, how much do the non-idealities affect what you're able to do? The reason I'm asking is because modern digital processes are highly optimized. Modern silicon processes are highly optimized to digital design, and analog designers just can't use them effectively.
Yeah, so it can sabotage the computation completely, and
Yeah.
so that's why this also relates to like the new application like machine. Sorry to go to that, but like machine learning, like they're noise tolerant, so it's a chance to use analog circuits to like some noisy compression, and then it's still usable. So that's the hope. Like in terms of if you want high precision computation, definitely still use digital. That's the only way to go. There's like a theory, like physical limit to show that too.
Yeah.
Yeah.
Thank you.
Oh,
Let's see. No. All right. So it'll take a minute, talk about emerging technologies, but then we still have the HDMI is still a challenge. So next I'd like to introduce Bingzhe. She is a fifth-year PhD student at University of Maryland College Park. Her research interests include optical neural networks and electronic design automation, and she'll be presenting her design framework for diffractive optical neural networks. And I will go ahead and let her get started.
Thank you. Thank you for the introduction. So today I'm going to present our work, LightRidge, which is an end-to-end design framework for diffractive optical neural networks. So nowadays, the digital computing systems is limited by the trade-off between the system throughputs and the power consumptions. However, the consumed power does not go totally towards your computing, and instead, a large part of the power consumption goes to the thermal dissipation. And the thermal dissipation is doing bad for the digital computing systems. It can cause thermal throttling and reduce the lifespan of your digital devices. And more importantly, it can cause the significant energy waste and big carbon footprints. So more and more studies are expressing their concerns about the problems brought by the development of the AI technology, especially nowadays, the AI model is getting larger and larger. So people start to think for novel computing solutions, like move to the light-based computing. The optical computing system is expected to provide high system throughputs at the low power consumptions. And this work is currently focusing on the diffractive optical neural networks, which is a kind of the free space optical computing system. And I will introduce the background knowledge by comparing it with the digital computing systems. So first, let's take the typical digital computing system, MLP, as an example. So the input of this MLP neural network is the vector of digital numbers, and the operators are the linear transformation and the nonlinear activation function. Data movements between the layers are realized by the digital computing, and the output of the system is also the digital numbers. And the hardware to deploy the digital computing system is based on the active transistors, which means you need to supply additional power for the transistors to work with the desired functionality. So on the other side, for the Yu-Neng system, the input information is encoded with a light signal, which is described with the light wave function. And the operators inside this system is light diffraction and the phase modulation, and the data movements is realized by the light propagations through the system, which happens by nature. And the output is the diffraction pattern with the light intensity distributions. And more importantly, the hardware to deploy the optical computing system is based on the passive optical devices. And this should be the big reason for its high energy efficiency. So let's get more details about the Yu-Neng system. So first, the information is encoded by the light signal and described with the light wave function, which is composed by two parts, the amplitude part and the phase part. And further, it can be described with complex valued numbers. And then the information encoded light signal is diffracted over the free space, over the diffraction distance. And at this point, we needed the mathematical approximation for the light diffraction modeling. And to compute such mathematical approximation, we needed the computation of the fast Fourier transfer and the inverse fast Fourier transfer. And this lighting diffraction is our non-trainable parameters of the system, as it is only related to the structure of the system, like the diffraction distance and also the system size. So after diffraction, the light signal will be phase modulated at each diffractive layer, and the phase modulation provided at each diffractive layer are our trainable parameters. So at this point, we need the computation of the complex valued matrix multiplication. So for a multiple layer constructed DON system, its forward function can be computed iteratively over the computation of the light diffraction and the phase modulation at each diffractive layer. At the end of the system, we will implement a detector plane to capture the diffraction intensity pattern. For example, for this classification task, we have predefined the detector regions for each candidate class, and we will pick the class with the highest light intensity captured in its corresponding detector region as our prediction results. So together with the ground truth label, we can compose the loss function for the training of the whole DON system. So at this point, we have modeling the whole DON system with differentiation. So based on this background knowledge about the DON system, we can have several challenges for the design and exploration of such a DON system. So the first challenge is the cross-disciplinary domain knowledge barriers. You need to know machine learning to construct your neural network and also optics to modeling the optical phenomena happening during this system, and also high-performance programming and the hardware software code design for optical emulation and optical hardwares. So the second challenge is the limited studies of the domain-specific code design to enable the seamless design to deployment process, especially for optical systems. So even though you can get very nice emulation accuracy performance, but when the trained model is deployed on the practical optical devices, the physical measurements is usually disappointing. So the third challenge is that we are in the lake of the high performance infrastructure designed specifically for the exploration of optical computing systems. Say, if you want to design a chip, you can have the automation tools from Xilinx, Cadence, or the open source, the OpenRoad, to help with the design process. And if you want to design your machine learning system, you can have the frameworks like PyTorch and TensorFlow to help with the design process. But we have nothing for optical neural networks from either design side or the application side. So we proposed our work, LightRidge, to connect the physical world and the computing system. So this framework provides the accurate and versatile system-level optical modeling, and also with the physics-aware code design algorithms designed specifically for the optical emulation and the optical devices. And also we provide the high-performance optimization and user-friendly DSL support for more people to use from, even though they are from different research backgrounds. So let's get started with your customized DON system. So first, install our package LightRidge with the simple pip install command. First, we need to initialize the inputs where we convert the digital numbers into the complex valued numbers as it is encoded with the light signal. And then we define our models by layer. So specifically to customize your layers, you just need to call our kernel functions inside this framework and put in your hardware information to customize the computing units inside your system. And then taking these customized layers into the network containers to compose your DON system. We also provided the training support and finally the hardware, the support for the DON model deployments. So this is an example for this hardware-specific DOM modeling. So first of all, let's start to define the layers. We take inside the hardware information, like the wavelength of the light signal is set as 532 nanometers, and the diffraction distance is set as 11 inches. And we use the specific hollow special light modulator to implement our diffractive layers, where we take inside the measurement list of this specific hardware and also the pixel size, which is the resolution of your hardware, of your optical hardware into our emulation parts. So after the definition, we stuck these layers together inside the network container to compose the whole system. So this whole design system is just as simple as building a machine learning model within the PyTorch framework. So LightRidge can offer the orders of magnitude speedups regarding the runtime compared with the baseline on either CPU platform and the GPU platform. We also provide the speedups breakdown to show that our framework can accelerate the kernel functions inside this system, including the computation of light diffraction and the phase modulation efficiently. Yeah. So based on that emulation of the exact hardware-specific DOM modeling, we further provided this end-to-end co-design prototyping to validate the whole system. So as you can see from the results, the experimental pattern matches pretty well with our emulation patterns. And we further provided the propagation patterns at each diffractive layer during the emulation process, which shows how the light signal is modulated to work as a computing system for the specific machine learning classification task. So based on this optical prototyping, we further provided the experimentally measured energy efficiency. So compared with the general purpose processor, this optical prototyping can have the improvements of 3 orders, and compared with the XPU, our improvements can be 50 times. So more importantly, the energy efficiency of the DOM system can be further optimized with the monolithic fabrication and with more advanced hardware setups. So besides the hardware setups in the whisper range, we can also do the hardware setups with the terahertz range. So where the laser system, where the laser source has a frequency of 0.3 terahertz, and the diffractive layers are implemented with the 3D printed face masks. And we also can help with the on-chip integration. For example, this is a monolithic on-chip 5-layer DOM system on a CMOS chip. So we can discover the system dimensions or the fabrication dimensions by the design space exploration engine provided in the LightRidge. And this deployment can be fabricated on the CMOS chip with the nano printing fabrication techniques. Okay, so further, so we also provided the flexibility for users to discover or explore their more advanced optical architectures. For example, in this all optical segmentation task, we implemented the optical skip connections between layers, and these can be realized easily by just customizing the neural network containers provided by our framework LightRidge. So the results shows our emulations can produce better segmentation performance compared with the baseline. So finally, so we will continue working on these projects actively. So we are open to any comments, contributions, or collaborations. So please keep an eye on our open source hardware projects, LightRidge. Thank you so much. Thank you.
All right, thank you for the great talk. If you have any questions, please line up. And if the next speaker could maybe get their AV situation figured out.
I'm Yu-Neng from Stanford. And I guess it's a clarification question. So I wonder the optimization you mentioned is like kernel fusion or like training the weights, or like there's some hardware aware kind of optimization going on.
Sorry, excuse, can you
Yeah, so I'm wondering the optimization you have in the framework is like, what's the optimization target you're having? Is it like training the neural networks or kernel fusion, or is like some optimization considering hardware non-idealities?
Yeah. So first of all, we do the kernel fusions and especially deployed on the CUDA tensors. And the second, we also do the how to say like the heterogeneous computing, and we take some of the computings on the CPU, but the most training part, which is the GPU really good at, so we take that part on the GPU part, so to accelerate the whole runtime process. Yeah, thank you.
See, thanks.
Thank you.
We have time for maybe one more question. Okay, I have a question that's not related to DSC. It's more of a question about optical neural networks. So you have to do an analog to analog conversion where you take visible light and you have to convert it into like a phase encoding of the image. Is there an efficient way of like, how is that done typically?
At the input or
at the input. So I suppose if I want to process, for example, you know, an image coming from the environment.
Yeah. So we just apply the face mask before the layers, and when the light propagates through this face mask, it can either encode it with the amplitude or the face mask. Yeah.
I see. So this part of the signal that you use is part of the encoding.
Yes.
Okay, interesting.
Yeah.
Okay, well, I'll welcome our next speaker. I'd like to introduce Zhou Chang. He is from CMU. He's a second-year PhD student. He's broadly interested in the intersection of space systems and computer systems, and will be presenting his work on designing nanosatellite constellations for high coverage, high resolution sensing. And I will go ahead and let him take it away.
Hi, I'm Zhuo. I'm a PhD student from CMU, and today I'm going to present Eagle Eye, a nanosatellite constellation design for high coverage, high resolution sensing. I'm going to explain how we do scheduling in space. So satellite images are useful for many geospatial applications, such as fire detection. It can help a firefighter to respond to forest fire, or ship detection to detect if there's illegal fishing or smuggling activity, or lake algae monitoring to protect human health and the environment. So previously, like those Earth observation satellites are those like large, expensive monolithic satellite. So here shows an image of the NASA Landsat 9 launched by NASA. And now there's a new trend, like people starting to use small and low-cost nano satellite. So this image shows a 3U CubeSat. It's a little larger than a coffee mug, and the total launching and manufacturing costs are also low. Like it costs like $100,000. And because of the low cost, like people are able to launch a large constellation of satellite. So by constellation, we mean a large group of satellites. So for example, Planet is a commercial company, and they have launched like 200 satellites for Earth observation. And actually, like nanosatellites are a new class of computing system with cyber physical constraints. So here we show the main components in a satellite. So the satellite would have an embedded CPU or GPU for image processing on board. And it also has a transceiver so that it can talk to the ground or talk to other satellites. And obviously, it has a camera to take the image of the Earth. And it also has some reaction wheel so that it can, so that the satellite can rotate and pointing the camera at a different direction. And it has a solar panel to get energy from sunlight, and has a battery and or capacitor to store the energy. And later we will show like how we design a scheduler to scheduling image capture under those physical constraints. So next we talk what are the requirements for such a satellite constellation. The first thing, we want the constellation can provide us with high resolution images. So here the upper image shows a low resolution image. You can still kind of tell like it's a ship. But for some applications, such as if you want to detect if there's illegal fishing or smuggling activities, you want a high resolution so that you can have more detail, like what's happening on the ship. And another requirement is like the target, like the ship or forest fire, they could be at different locations of the Earth. So we want to provide a high coverage of the targets. And unfortunately, we find that the existing camera cannot achieve both high resolution and high coverage. So here we show like one satellite flying forward and take images 1, 2, 3. And we carry two properties. The first one is like the coverage, which is defined as like how much like area the image can cover of the Earth. And another thing is the resolution, like how many pixels are in there, like in the image for every square kilometer. And actually, there's a relationship between those two. Like the coverage times the resolution is the total number of pixel count in the camera sensor, which is kind of like physically constrained by the camera. And we find like 9 existing satellite cameras, and this figure shows their resolution and the coverage. And we can see that those existing cameras, either they have a high resolution or like they have a high coverage, but they cannot achieve both. So next, we talk about our system Eagle and show how we can achieve both high resolution and high coverage. So at high level, like our system uses a heterogeneous constellation. So we have a leader satellite and one or multiple follower satellite. They are flying at the same orbit and the same altitude, but the follower satellite will be like a few distance behind the leader. And the leader are equipped with some with the low resolution cameras. And as the leader flying forward, it will take the low resolution images of the Earth. And the leader has some onboard computation, and it can run some machine learning model to process those images and to detect the target. So here, those red box shows like some ships detected by the leader satellite. And the leader satellite will send the target location to the follower satellite using the wireless communication. And the followers are equipped with some high resolution camera so that they can point the camera toward those targets and get some high resolution images. So next, we talk about what are the constraints for the system. There are 2 constraints. One is the acquisition, and that is the compute constraint. So first one, for the acquisition constraint, for the follower satellite to take an image of the different targets, because the targets are at different locations, so the satellite need to like rotate to pointing their camera at a different angle. And we need to make sure like the angle between those when you imaging different target that the alpha is less or equal to like the max rotate angle provided by the reaction wheel. And another thing is like when the satellite flying over the target, it can take the image of that target from different angle. And ideally, we want that looking angle to be small, because if the angle is too small, too large, like the image is kind of distorted and not very useful for the application. So there's a time window in which we want the satellite to take the image. The second constraint is about the computation. Like because the satellite are moving very fast, like the ground speed is around like 7 kilometers per second. So new image comes in also very, very quickly, like every 15 seconds, or there will be a new images. So for each image, the leader satellite needs to do two tasks. The first one is that it runs the machine learning model for the target detection. And then I need to do this acquisition scheduling to decide what is the order for the followers to take high resolution image of those targets. And to make things worse, as we mentioned before, like the satellites are small, they only have like a embedded CPU or GPU. So previous work has showed that for the first step, like the target detection, there are work from the ML side and from the system side to reduce the runtime. But unfortunately, for the second step, like the acquisition scheduling, we find that the existing schedulers still have very long runtime. So here we consider one existing scheduler is called anytime branch and bound. And this figure shows the runtime with different number of like targets to be scheduled. And the red line shows like how many, the red line shows like the frame deadline is like every 15 seconds, there's a new image comes in. And from this figure, we can see that when there are like more than 22 targets, the runtime be very high, would be like more than 60 seconds. So what this means is that suppose like there's one like low resolution image and there are lots of targets in it, and like after every 15 seconds, there's new image comes in. But because like there are so many targets and the scheduler is too slow, like the scheduler is kind of like stuck in the first image and it has to skip, it cannot process the rest of the image, and this would result in some missing target, and which means like a lower coverage. So next we talk about our solution. We have 2 main ideas. The first one is the target clustering. So considering like there's a low resolution images, and the machine learning model would generate lots of like the bounding box, each of them corresponding to a target. So one strawman solution is that you can ask each follower to take one high resolution images for each target. And as you can see, this needs lots of like the high resolution images, and lots of them have lots of overlap, which is a waste of resources. So our idea that we can kind of like clustering those targets to minimize the number of like high resolution images needed to cover all those targets. And the second idea is that we can formulate the scheduling as a traveling salesman problem. So here we considering like suppose the satellite need to like to take image for 3 different targets, and we can construct a graph. So each node corresponding to one target, and each node have a value. The value means like how many targets are in that images. And we can compute the acquisition time between different targets. And those acquisition time also corresponding to like the distance between the node in the graph. And note like the acquisition time from two different directions could be different, because one way when you are flying forward, like that way will like take less time. And also, like we mentioned the time window before, like only during that time window, you can take the image of the target. And this time window could also like be put into the graph, like means only during that time window can the salesman like visit that node. And the goal here is that we want to maximize the total number of like the visit value. And but after we have this graph, this is like an existing traveling salesman problem, and there are like an existing highly optimized solver to solve that problem. Okay, next we talk about some evaluation. We're considering 3 different applications like ship detection, lake monitoring, and airplane tracking. And we get the location of those targets. There are different locations of the Earth. And because we don't have the money to launch all those satellite constellations, so our evaluation is carried on based on the simulation. So those red dots shows some target location, and we simulate how where is the satellite location over time. So those yellow lines shows the satellite ground track, and we can compare the ground track with the target location to see whether that target has been captured by the satellite. So we considering 3 different systems. The 2 baseline system, one is like the low resolution only constellation that we considering it has like a 20 satellites. All of them are equipped with low resolution cameras. And the second baseline is like a high resolution only constellation, like also has 20 satellites. All of them have like high resolution cameras. And finally, it's our system Eagle Eye, like we have 10 low res and 10 high res. So this figure shows the coverage and the resolution provided by all those systems. So we can see that the blue dot shows the low resolution only constellation, and they have a high coverage, but like they only provide you a low resolution image, which is not very useful. And we can compare like the green dot and the yellow dot, and we can see that Eagle Eye achieve like 2 times higher coverage than a high resolution only constellation. And for each system, like there are 3 dots, they are corresponding to the 3 applications we mentioned before. And in the paper, we also show that our system Eagle Eye achieve like a much faster scheduling runtime than the previous solution. And we have more results in the paper. We show that Eagle Eye can handle like moving targets, and the best like follower count depends on the target density. And we also show that if you put both high resolution and low resolution cameras at the same satellite, you cannot achieve like as high the same coverage as the Eagle Eye. Okay, so this ends my talk. Like for our project, we find that the existing system cannot achieve both high coverage and high resolution. And we propose Eagle Eye, which is a heterogeneous constellation, and we propose 2 solutions to reduce the runtime. And finally, we show that we achieve like a 2 times higher coverage. Thanks. I'm happy to take questions.
All right. Thank you for the talk. Please line up for questions. We have a few minutes before the next talk. So, and if the next speaker wouldn't mind getting set up. Okay, well, I have a question. So are these satellites, they communicate, there's inter-satellite communication, is that correct? Are there any challenges associated with having satellites communicate with one another? Like, do you have to turn on and off the receiver, or is it, I mean, how close to free is this communication channel?
Yes, but because like for our thing, we only need to send like the target location across the satellite, and the target location, we assume will be small because for each target is like a few bytes. So
I see. So you can get away with sending like 1 packet.
Yeah.
But are you ever worried about the amount of data?
Yeah, because I like the total amount of data should be small, like a few bytes, and the wireless communication, I think the current one can achieve like a few kilobytes per second. So
okay. And then my other question is, you solve a TSP problem to figure out, I suppose, so the nodes in that problem are, remind me again?
The nodes are like corresponding to target.
The targets, okay. So how many targets do you typically have to solve this problem for?
Like, because after we do that target classing, there are maximum like like 100 target also. That would be not too many targets.
I see. So it's pretty tractable.
Yeah.
Thank you. And are there any other questions? Yes.
So you have 10 high, 10 low, right? Do you have any DSE result in the paper? Like maybe you do 5 on high and 5 on like 10 on low resolution.
Yeah,
or
in the paper
15 or 5. Something
yeah,
like that.
in the paper we discuss like what is the best configuration.
So is
for
10 the best?
For the most of the scenario, you only need one follower for one leader. But if the target density is high, like
Oh, that's
for
why
ray
it's 10,
tracking,
10
yes,
is
you
offering
need
really good
more
result. Okay.
follower, it will give you higher coverage.
I see. All right. Thank you.
All right, thank you. Next, I'd like to introduce Reese Gretsch. He is a third-year PhD student from University of California, Santa Barbara. He is broadly interested in emerging technologies and non-traditional computing paradigms, and he'll be presenting his work on performing efficient arithmetic operations with temporal computing. And I'll go ahead and let him take it away.
Thank you. Yeah, I'm presenting our work on energy efficient convolutions. And so generally, we're targeting fusing sensors and compute, because right now the paradigm is a sensor captures data, potentially a large amount of data, transfers that over some link that consumes energy to memory, and then accesses that memory, consuming more energy, and then finally does the computation. Whereas there are systems that try and merge these two, right? Where we generate data, compute on it immediately, and then transmit less data off to memory, and then we can store it and use it later. Right? And this has been known to have many benefits for embedded systems, including reducing of data movement and decreasing response time. However, the current paradigm is using analog computing for this. But that's difficult because analog computing requires a lot of domain-specific knowledge, as we heard earlier, and it scales poorly, right? And camera systems have potentially millions of pixels. So we want something that scales very well, but it's difficult with analog. So our solution kind of lies in the middle of analog computing and digital. We have what's called temporal logic, where we encode information into the rising edge of a voltage pulse. This gives us the expressibility of analog, but because we're using a single wire with a binary value, we can use all of the digital building blocks. For instance, the min operation can be implemented using an OR gate, and an AND gate can be used to implement a max, right? And then we can use inverters to implement delays. So we have the best of both worlds. But general arithmetic has been shown to be very difficult in this domain. And beyond that, we also have trouble storing things. So we kind of assume everything arrives all at once, but most sensors don't do that. Right? So in this work, we demonstrate a framework for general purpose arithmetic. And then we present a novel method for reusing data across cycles. And we take these two innovations and tightly couple them to a camera system to provide energy efficient convolutions. And so this all starts with the major innovation of our work, which is delay space. We do this negative log transformation of all of our values and all of our operations. And the first major thing that this gives us is important value inversion, right? Where a high value that might carry a larger importance to a computation arrives earlier, whereas a small value arrives later. So we can potentially approximate it or ignore those small values. And then we also transform all of our operations. So multiplication becomes addition, which we can implement using simple delays in the temporal domain. But addition and subtraction become these kind of wonky functions. The first one's called negative log sum exponential, and then second is negative log difference exponential. And it turns out that negative log sum exponential is also known as the real soft min. So if you have two inputs and the two inputs are very far apart from each other, it is min exactly. But if we're trying to use this min approximation, as the two values start to get closer to each other, we start to get a much larger error, right? And all of the information is in this kind of error. But what we found is you can actually take a max term, something we can implement with an AND gate, and do a little bit of shifting. We can combine a max term within our min approximation and start to get better accuracy. Then we can kind of replicate this. We can control where we place our min terms to get arbitrarily close to this NLSE function. Right? And this hardware is actually pretty simple. We use a bunch of AND and OR gates, or first arrival, last arrival gates. And the only analog thing here is the delay elements. But as I mentioned earlier, we can use inverters for the delay elements. So we have a fully digital way of doing this nonlinear function. So that gives us some arithmetic. And we also find out a way to do subtraction. But if you want more information on that, you'll have to read the paper. But with convolutions, we use multiply accumulates. And accumulation implies memory, right? But as I mentioned earlier, that's kind of difficult. So how do we handle values that arrive across clock cycles? The first kind of naive approach is to use a ton of delays to synchronize everything. So if we know all of our inputs ahead of time, we can just delay everything so it appears like everything arrives at the same time, right? But this requires one knowing how much we have ahead of time, and it consumes a lot of delays, right? So if we're in the millions of pixels range, this is millions of delay elements, and that gets expensive both in energy and area, right? So our proposed approach is recurrence. So we take every single rising edge of a voltage and convert it to a more shorter pulse that dies at the end of the clock cycle. This allows us to collapse our representation onto a single line. And now we can just pass this line into some logic. Right? I have to flip it around. So visually, we're passing the first thing in first. And the first cycle is not all that interesting, right? We just pass it through and it's feed forward. However, in order to operate with the next cycle, we can use a delay line or a delay element so that we can resynchronize this output with the next input, right? And now we can operate on these two together, right? So we essentially created a temporal register, right? Solving some of the memory issues, right? And now now we have all we need to implement a rolling shutter camera architecture. And so the way modern cameras work is they read a row at a time, right? So the first row comes in and we want to do all of the computations on that row. And then when we're done with that computation, because we're accumulating with some of the information from the next row, we need to recur back some of the previous cycle's information, right? And so in this architecture, we actually hard code all of our wait delays and all of our accumulation units. But in order to do that, every time we read in data, we have to actually orchestrate where that data goes, right? If we have multiple in-flight accumulations, we have to do some cycling. However, because we're using all of the digital building blocks, we can also use digital logic for control. So we can use just the same, Verilog to design the control as we can with everything else in the system. Right. So now when we go to evaluate our system, the first thing we evaluate is our approximation accuracy. Right? And so what these graphs show is as we add approximation terms, so as we add maxes to our min approximation, we improve in accuracy. That's about what you would expect. So on the left, we show an idealized version. And so we get diminishing returns, but eventually we will reach pretty close to 100% accuracy. The right graph shows what happens when we introduce noise, right? And so noise causes us to cap a little bit, where on this graph, as you look down, we're adding noise. So our accuracy drops as noise increases, which makes sense. However, even in a noisy environment, which is this bottom line there, we can still achieve up to 96% accuracy, which is pretty good. And then we do some SPICE simulations of these delay elements to create a model for energy. And then we create a simulator so that we can get a full accuracy, area, time, and energy for any given convolution architecture. Then we compare it to an analog approach that's called processing in pixel. And we show that, one, we improve the energy efficiency. And when we improve the energy efficiency the most is when we start to grow up in convolution size, but the stride doesn't change, right? So this kind of illustrates that the analog computing approach struggles to scale, whereas our approach scales very well. Then on top of this, our energy delay product is several orders of magnitude better than theirs because we're able to leverage the rolling shutter. And so that the last cycle that we capture in the frame, we are done with our computation that cycle, and we can move on. And so in conclusion, we leverage some emerging computing domains, functional approximation, and the rolling shutters of cameras to achieve over 1,000x improvement in energy delay product for fused convolutions. Thank you.
Great talk. We can now take some questions. Anyone wants to line up?
Hi, Luke from Stanford. Thank you for an interesting talk. Could you elaborate more on the motivation for write that minus logarithm term? Because like you make one operation easier, but one harder. So could you elaborate?
Too many transitions. Yeah. Yeah. So, right, as I mentioned, there's an error between the orange line and the blue line. And so this max, this is shifted down max, is actually very easy to implement, right? This introduces these delay elements here, and we add just a couple of AND gates to go with them. Now, if you read the paper, you'll see that we're actually not doing this subtraction. We add a constant term so that there's no subtraction in this, and we're just using delays. But then that constant term we can actually subtract out when we do our recurrence later.
Oh, I meant like for the need for this approximation is because you write that x to minus log x. Like could you elaborate on why you do that? Like what's the reason behind it?
Why we do the transformation?
Yeah.
Okay. Yeah, so multiplication in temporal logic, right? So addition is delays. Multiplication would be repeating a delay n times based off of the value you're multiplying, right? One, that's hard to do. The analog approaches right now are very difficult and introduce way more noise than we normally would have. And it also significantly slows down our system. So if we can transform the multiplications to delays to a single addition, then we're much faster.
I see. Thank you.
Other questions? Okay, I have a few questions. How do you convert into the importance space in the analog domain?
Into importance space or into delay?
Oh, sorry, delay space. Yeah. So importance space is the original operation.
Yeah.
Right? And so that's what's coming out of the photodiode, I'm assuming?
Yeah.
Okay.
Yeah.
So
delay space, so importance space to delay space. So sorry, voltage to time is typically handled by what's called a starved inverter, which lengthens the time it takes to go from that inverter. And the way we normally do it is we do a lot of kind of analog mixing to make sure it's as linear as possible. However, the starved inverter provides a 1/x, so an inverse relationship, which already somewhat closely matches this negative log transformation. So you can approximate negative log using a starved inverter that we already use for voltage to time conversions.
I see. So you're doing like analog to analog conversion, and it's also applying the operator at the same time.
Yes.
Got it. And then my second question is, so you have this interesting register architecture where you could basically feed in a pulse and then loop it and recycle it back into the system. So if let's say you have a value that you're accumulating for a long period of time, does anything accumulate? Like does error accumulate, for example? Or I guess I'm just wondering about like what the relationship is between the longevity of a value and the fidelity of the value you're representing.
So like that's a difficult question to answer.
I know.
So if you assume all noise is independent,
Okay.
then actually that noise doesn't really accumulate as much because yeah, it grows as 1/square root of n, which is not much compared to the actual value itself. But if you assume there's some correlated noise, then it grows worse. And we haven't really quantified that.
I see.
Yeah.
So with under certain noise conditions, the accumulation is not bad. And then like if you have some sort of like biasing or like correlation between like noise terms, then okay, I see. Cool. Thank you. Other questions? You have 2 minutes. All right. Well, I'd like to invite our speakers to hang out for a bit in case people want to take some questions offline. Otherwise, I think we can adjourn this session. Yeah. So thanks for coming to the Emerging Technologies.